for the grade 12 chemistry class of the St. Peter's College, Colombo, Colombo branch. In this video, we are going to study about the group 18 elements. First, let's see what are the group 18 elements. They are helium, argon, neon, krypton and xenon. Now, we have to consider about the group trends. As you know, all the group 18 elements are noble gases. So they are unreactive and monoatomic gases. Only xenon forms the compounds. And also group 18 elements have positive electron gain enthalpy. Because as you know, all the group 18 elements shows the Ns2 Np6 electron configuration. That means they have already completed their octet statements. So to get new electron, they have to form a new shell. So the electron, to get electron, they have to use a big energy, so that they show positive electron gain enthalpy. Now let's take the properties of group 18 elements. If you check the properties of group 18 elements, as I show you, you can see the Ns2, Np6 electron configurations and also atomic radius, first ionization energy and electron gain enthalpy. Here you can see all these values are decreased when we go from top to bottom of the group 18. Because when we go from top to bottom, we can see the atomic radius increase. So all these values decrease. As I told you, only xenon form the compounds. Xenon form compounds with fluorine and shows the oxidation states of +2, +4, +6 and +8. If we check the compound and structures, here this is the structure and this is the oxidation state and this is the compound. Here you can see non-bonded p orbitals we can find. If we take the first one, it shows the oxidation state of +2, that means it consists non-bonded 6 electrons. So these are that non-bonded p orbitals. So all these structures, you can see that if there are non-bonded electrons, we can see that in orbitals. After the group 18, we are going to consider about the periodic trends shown by the S and P block elements. Here I have shown you all the S block and P block elements. In blue color, you can see the S block elements, and in yellow color you can see the P block elements. In vertically, we can find groups, and in horizontally, we can find periods. So in this part of lesson, we are going to focus on the valence electron configuration of S and P block elements, metallic character of S and P block elements, and acid, base and amphoteric nature of oxides of period 3 elements. In red color box, I have shown you the period 3 elements. In this part, we are mainly going to focus on the period 3 elements. Then reactions of third period oxide with water, acid and bases. After that, acid, base and amphoteric nature of hydroxides and hydrides of group period 3 elements, and nature of halides across the third period elements. First, let's take the valence electron configuration of the S and P block elements. If we check the group number and number of valence shell electrons, we can see this pattern. The group number is equal to the number of valence electrons in the valence shell. If we take the group number 1, all the elements in group number 1 consist 1 electron in their valence shell. Group number 2, 2 electrons. Then we have to consider the group number 13. Here you have to take only the number 3. These elements consist 3 electrons, and number 4, 4 electrons. Like that, there's a pattern, and you can easily remember the number of valence electrons if you remember the group number of that elements. Now let's take the metallic character of S and P block elements. When we go across the period, we can see the metallic nature decrease, and when we go across the group from top to bottom, we can see the metallic nature increase because the atomic radius increase across the group and atomic radius decrease across the period. So this is the reason for the nature of metallic character. Now in here we are going to consider about the third period elements, the melting point and bonding time, how they colorate, how melting point and bonding type colorate. If we take the values, melting point from sodium to aluminium, you can see here decrease, and silicon shows the highest value. From sodium to silicon, melting point decrease, and after that from phosphorus to argon, the melting point gradually decrease. If we check the bonding time, sodium, magnesium and aluminium shows the metallic bonding type, and silicon shows the network covalent bonding type, and after that other elements show the covalent bonding type. So in here silicon shows the highest melting point, and also it shows the network covalent bonding type. As you know, normally the network covalent compounds consist higher melting points than the other elements. So the third period shows a gradual increase in melting point and then decrease across the period. Now in here we are going to discuss about the acid, base and amphoteric nature of the period 3 oxides. This is the table. You can compare the oxidation number, bonding type and nature of that oxide, whether they are acidic or basic. If we take oxides, first three elements shows the ionic bonding type, and silicon dioxide shows the network covalent bonding type, and other three elements shows the covalent bonding type. Then basic nature, if we take the basic nature, the first two elements show the basic nature, and aluminum hydroxide shows the amphoteric nature. If you can remember, when we study about the group 13, we studied about aluminum hydroxide. It shows the amphoteric nature. That means it shows both acidic and basic nature. Then after aluminum hydroxide, silicon hydroxide is a weakly acidic, and gradually the acidic nature decrease when we go to left side, right side. So you can easily remember these bonding type and acidic or basic nature directly correlate each other. Now let's take the reaction of third period oxides with water, acids and bases. Oxides of sodium and magnesium react with water and form the relevant hydroxide, and these hydroxides react with acids and form the relevant salt and water. So we can see, if we tell these oxides are basic and these oxides should react with acids. So we can prove that here these oxides react with acid and form the salt. So normally we use these reactions to prove the nature of the oxides, whether it is acidic or a basic. Now let's take the aluminium oxide. As I told you, it is an amphoteric oxide, and it reacts with acid and form the aluminium chloride, and also it reacts with sodium hydroxide, that means it is a base, also react with base and form the relevant salt. So we can see here the amphoteric nature of aluminium. It reacts with acid and also react with base. Then silicon dioxide is weakly acidic, and it reacts only with strong bases, but silicon dioxide not react with water. After silicon, phosphorus, sulfur and chlorine we find in the third period. So these are the reactions of that elements with water, and also the reaction with bases. So we can see here these oxides react with water and form the acidic compound H3PO4, H2SO4, HClO3. All are acidic compounds. And also these oxides react with bases and form the relevant salts. If you check these reactions and the products, you can understand that. So we can prove these oxides are acidic. Now we have to consider about the acid, base and amphoteric nature of hydroxides and hydrides. This is the comparison of third period hydroxide. It is also as same in the oxide. We can see basic hydroxide in left side and acidic hydroxide in right side. And aluminium hydroxide is a amphoteric hydroxide. So one type also as same in the oxides. One type correlate with the nature of the acidic or the basic nature. Now let's compare the third period hydrides. If we take the nature of aqueous solution, sodium and magnesium hydrides are basic and aluminium hydride is amphoteric and silicon hydride is very weakly acidic, and when we move to right side we can see the acidic nature gradually change from weakly acid to very strong acid. Now hydrides of sodium and magnesium react with water to produce solutions. We have to consider about that now. How these hydrides react with water. Sodium, magnesium and aluminium hydrides react with water and form the relevant hydroxides and hydrogen gas. And if we take the pH3 or phosphorus hydride, it is weakly soluble in water and produce the neutral solution. After that, sodium, magnesium, aluminium, phosphorus, then we find the sulfur and chlorine. And sulfur and chlorine hydrides, H2S and HCl, react with water and form the acidic solution. Here you can see these three hydrides form the basic solutions. Then pH3 is weakly soluble in water and form the neutral solution, and sulfur and chlorine hydrides form the acidic solution. So you can find the pattern of the gradual change along the third period. Now let's take the nature of halides across the third period. So as the electron negativity of the elements increase along the third period from left to right, the ability of hydrolyzation of chlorides increase, because the electron negativity increase and also the hydrolyzation ability also increase. So we can check that with this chart, the comparison of third period chlorides. Here bonding type, first two chlorides consist ionic bonding type and other chlorides consist covalent bonding type. And if we consider the nature of aqueous solution, sodium chloride, as you know, is a neutral solution, and magnesium chloride very weakly acidic, and other chlorides, aluminium, silicon, phosphorus and sulfur chlorides are acidic. So you can compare these uh, values in the third period. When we take the reactions with water of third period, covalent chlorides as follows. Here we can see third period covalent chlorides, aluminium, silicon, phosphorus and sulfur react with water and form the uh, relevant products. Then variation of properties down the group. Down a group, the ionization energy decrease and metallic nature increase. Down the group, ionization energy decrease because the atomic radius increase and the ionization energy decrease, and also metallic nature also increase. Uh, we can take group 15 to show that because in group, if we take the group 15, you know, nitrogen, phosphorus, arsenic, antimony and bismuth are the elements in group 15. And if you take the physical state of the elements, we can see nitrogen, phosphorus are nonmetals and produce acidic oxide. Arsenic and antimony oxides are amphoteric, and also bismuth oxide is basic. So by taking that details, we can prove that the metallic nature, uh, you can see the metallic nature increase when we go from top to bottom of the group. This is same for the all the groups of S and P block elements. Now here I have shown you the reactions with water of group 15 halides. As I told you earlier, the group 15 elements, these are the group 15 halides, and when you consider about these reactions, you can see how they react with water and uh, what are the products they form. Normally you can see in all reactions they form HCl, and also uh, here on ammonia normally is shows basic conditions, but all other products show acidic conditions. So by considering these reactions, we can deduce that metallic nature increase when we go down from top to bottom of the relevant groups. These are the important things about the group trends of S and P block elements, and I hope to talk with you in our future videos about the D block elements. Thank you.